particles. And so as we do that, we can use laboratory experiments, but we can also use various cosmological probes that I'm going to focus on today. And in a sense, we can unpack the very same interactions between dark matter particles and the standard model particles and normal matter, just like we do in direct detection experiments that have traditionally set the best possible, limits that we have so far on standard, dark matter paradigms like the WIMP and so forth. So I'm going to, in a sense, talk about something that you might call cosmological direct detection. Now, dark matter physics, its masses, the masses of these particles, but then also their interactions affect cosmology in a variety of ways. And so this is a diagram that I like to think of when I think about what are all the things we can look in cosmological data sets to look for something that indicates, that points towards new physics by dark matter. And so on the one hand, dark matter contributes the energy density in the universe. So depending on how the masses of these particles, what the masses of these particles are, that contribution can be that of a relativistic fluid or that of a non-relativistic fluid. And so dark matter particles can affect the expansion history of the universe. Then they can also interact with normal matter. And if they do that, which is beyond cold dark matter, beyond CDM physics, if they do that, they can put baryons, hydrogen in the universe, in thermal contact with dark matter. And so they can change the thermal history of baryons, and the thermal history of dark matter could be different from what we imagine in standard cosmology. And then finally, if you have interactions between normal and dark matter, you can alter the distribution of matter in the universe, both of dark matter and that of baryons. And so you can look at tracers of structure to look for, evidence of this new physics. And so the equations here are not for you to skim and immediately get them if you're not used to looking at them there. But for the cosmology aficionados out there, momentum transfer between dark matter and baryons is captured in these additional terms in the usual Boltzmann equations. And typically in standard cosmology, we imagine that the dark matter temperature is zero effectively, whereas if we put dark matter and baryons in thermal contact, we make them interact with each other, then that temperature rises and a lot of observables can change accordingly. So for the most part, you're seeing now, I'm actually going to be talking about dark matter baryon elastic scattering. So the very same physics that we look for in laboratory experiments as well. This is my only particle physics-y slide. So bear with me. I want to give you a little bit of meat behind all this story that's going to largely boil down to observations. So when we think about dark matter baryon elastic scattering, in cosmological context, we're often inquiring about scattering of non-relativistic dark matter particles with, let's say, protons or neutrons and so forth. And the most generic question that you can ask is, what are the operators at low energies, at non-relativistic energies that I can write down self-consistently, mathematically, that describe such elastic interaction? Okay, and so particle physicists do this kind of thing. It's called the effective theory of dark matter baryon interactions. And within the effective theory, you write a whole bunch of operators down. They depend on the mass of dark matter particles and the interaction cross-section. And then if you are an experimentalist looking for collisions of dark matter particles with baryons in direct detection experiments, maybe you are really interested to measure recoil energy of nuclei that are your targets that you hope dark matter will slam into. But if you're a cosmologist, you really don't care about individual interactions. So in a sense, the only quantity that you really care about is what's the total momentum transfer. And so what's the total momentum transfer interaction cross-section? So how much momentum and heat is transferred between dark matter and baryon fluids overall. And so when you average the interaction cross-sections, which are usually those differential cross-sections that depend on the angle and so forth, when you average them over angles and you integrate over velocity distribution, really the only thing that matters is what's the velocity, relative particle velocity dependence of your momentum cross-section. So all this to say that interactions could depend on relative particle velocity. We know one such example is, for example, Coulomb interaction, right, between electrically charged particles in the standard model. So I'm allowing simply here my interaction to take any power law dependence of the relative particle velocity in attempt to be as generic, as general as possible in how I treat what we might understand as theory from particle physics. So I'm allowing all possible phenomenologies in this simple parameterization. And then my unknown, the thing that I really want to measure not to be zero at some point in the future and hope to discover, new physics, is this normalization to the cross section. Okay, so far sigma naught in all the data sets, spoiler alert, is consistent with zero for the most part. But that's the parameter whose measurement would signify a discovery of the interactions in cosmological data sets. And then again, if just in case you do, deal in Boltzmann equations, the momentum transfer rate will depend on the interaction cross section. And then it'll inherit some knowledge about how this interaction depends on particle relative velocities, velocities between dark matter and whatever baryonic particle it's colliding with. And in cosmology, for the most of cosmic history, relative particle velocities are sourced by thermal velocities. So this is how my temperature pops into this equation. And here is that power law index n, which for velocity independent interaction would be zero. And then you can plug in any number your theory gives you in there as well. So for the most part, the temperatures will matter in terms of how much momentum transfer between dark matter and baryonic fluids there are under a given theory. Yes?
Is there any significant variation for the cross-section depending on the baryon you are?
Yeah, so I'm not assuming any a priori magnitude of the interaction cross-section. I'm very agnostically approaching, the question of how large is this cross-section allowed to be, right? So I'm not assuming any particular, UV complete model of particle physics to aim at a particular cross-section. Like you might think of if you're thinking about the bullet cluster and so forth. We don't have any priors of that sort. Yeah, thank you for the question. If people on Zoom have questions, just shout out. I'll be happy to stop. All right, so I want to show you the cosmologically relevant quantity when we talk about dark matter baryon scattering in cosmological context. So that's this momentum transfer. So I'm plotting here the momentum transfer rate normalized to the Hubble rate, okay? And I'm plotting it for a bunch of different velocity dependent interactions, all normalized to the current Planck limits for that interaction. And so what I want you to see from this plot, what I want you to take from this plot is that most of the action for most of models happens in the early universe at high redshift. Okay, so most of the interactions will have a larger cross section when the temperatures are higher in the universe, and most of them kind of taper off in the late universe. Tony.
So what are you using for the temperature? Is it the temperature of the universe or is there a different temperature?
Yeah, so what I did for this plot is we evolved the temperature of dark matter from zero, from the initial condition zero, and just let it couple to baryons and let it evolve however it wants. And very, very quickly they thermalized for such large interaction cross sections at early times. So dark matter and baryons end up being thermally coupled at early times. Yeah.
Is there a characteristic redshift I should think about when dark matter and baryons decouple?
Yeah, so that depends on the interaction cross section. Okay. What I'm showing here is I've normalized all the cross sections to the Planck limit. Okay, so I haven't used any. We have better constraints to that I'll come to in a second. But if you put a bound from Planck data, the reason all of these models bunch up in this one spot around 10 to the few times 10 to the 4 is because that corresponds to the sensitivity of the CMB. Okay, so they're all pinched in one point, whereas all of the lines to higher redshifts are just kind of extrapolations from that measurement under a given model. Yeah. Okay, good. So just to recap what I said, for positive powers of velocity dependence in the interaction cross-section, most of the action happens at early times, but if you have something like a Coulomb interaction, velocity to the -4th, between, let's say, a proton and a dark matter particle, then the momentum transfer starts to pick up at later times. So the interactions start to change your cosmology in the later universe after recombination. So depending on the model, action happens at different points in cosmic history. So it's kind of convenient to think about this as, if we're looking agnostically for this new physics, interaction physics, we may want to scan through cosmic history because different models pop up at different times.
Sorry, one more question. So Coulomb is -4, you said, and what a typical weak interaction, what would that mean?
I don't know what the weak interaction will boil down to, but if you have, for example, positive powers of velocity dependence, like the square and the fourth, this would be something like the interaction with the electric dipole and a magnetic dipole and so on. Yeah. The weak interaction typically has very strong temperature dependence. Yeah. All right. And then once you have these operators, you can figure out momentum transfer as a function of redshift, as a function of temperature. And then, you can imagine that can then help you figure out how this momentum transfer alters the clustering of matter as measured by the matter power spectrum, P of K, or by the CMB anisotropies in the CMB power spectrum, CL, or how the temperatures of these fluids are altered in these cosmologies with interactions. Okay, so that was my theoretical introduction. This is the roadmap of the rest of the talk. So I want to touch on a few probes of this dark matter interaction physics. And I'm going to touch on also dark matter particle mass and how we learn about the particle mass in a model independent way as well. And I want to start from near field. I want to talk about the probes that have to do with structure within our own Milky Way, and then move on to large scale structure in 21 centimeter cosmology. And if I have time at the very end, I'll tell you a little bit about what we've learned from Big Bang nucleosynthesis, also about the same physics. But the objectives of all of this are, let's measure the mass and the interactions of dark matter particles. Okay, so I'm really here representing a whole bunch of people in my group, and also a whole bunch of collaborators here at Carnegie and elsewhere. So I want to just point out a lot of the work this guy over here has done. So I have a lot of backup if there are questions I can't address. And I will also highlight Karima Mari and Trey Driscoll, who have done a lot of the work that I'm going to show the results for here today. The rest of the collaborators are also listed there. Andrew Benson is among them as well. All right, so starting with near field cosmology, I want to show you what we've learned from the smallest galaxies. And this is going to be work that's a couple of years old, but we're thinking about some new spin-offs on it. So I would like to start there. So when we think about measuring the distribution of matter in the universe, for our cosmologists, it kind of boils down to reconstructing this matter power spectrum. And here I'm showing specifically the linear matter power spectrum. And of course, there's a whole bunch of visible tracers that let me put data points on top of this theoretical curve. We've done a fantastic job with CMB experiments in measuring the very large scales. But these days, most of the action that's really interesting in terms of dark matter physics is happening on small scales, on large Ks. And those small scales are best mapped with small scale structure and with things like substructure within our own Milky Way. So I'm going to show you some of the work that relies on looking at satellite galaxies, populations of satellite galaxies within the Milky Way to constrain dark matter physics. And the observational backdrop to all of this story is that currently we have amazing surveys like the Dark Energy Survey and DESI, upcoming the Rubin Observatory, the Roman Space Telescope, and then also a whole bunch of CMB experiments that are likewise looking to measure lensing on very small scales. They're looking to resolve the CMB sky better than we've ever been able to do before with Simon's Observatory and CMBS4 as well. All right, so why small scales? So it turns out that dark matter microphysics, those interactions, and even the masses of dark matter particles tend to mess the most with smallest scales, with the structure on smallest scales, which is not so surprising when you think about that, the smallest scales would have been affected by particle physics and particle interactions at early times, and then they eventually gave seeds for what became the structure in the local universe. And so here's a quantity that I'm going to stick with for a lot of the rest of this talk. It's the transfer function, which you can think of as the ratio between the linear power spectrum in a cosmology where I put some new dark matter physics normalized to the CDM cosmology. Okay, so this is the difference that dark matter physics of various flavors makes on the linear matter power spectrum. Okay, so your standard warm dark matter is the red line here. You have a cutoff because structure is washed out on smallest scales because dark matter inherits some velocity from early times. It's a thermal relic, and it cannot cluster below a certain scale. It moves too fast. If you have dark matter that interacts with protons in a velocity independent manner, then you have the dashed blue line, which is very similar to warm dark matter. If you have dark matter, fuzzy dark matter with a significant de Broglie wavelength, you end up with a cutoff of a slightly different shape. But in all of these cases, very different physical processes imprint a very similar signature within the distribution of matter on small scales. Now, there are two ways I like to think about the information from this transfer function. Again, as a cosmologist, thinking for the moment in linear theory only, I can relate the scale on the bottom to the mass of the halos that would, roughly speaking, form from Fourier modes in perturbations on a given scale. Okay, so I can, in linear theory, relate the mass of the halos to the scale from which they would roughly form. Of course, there are nonlinearities when gravity is important. And so this mapping is not perfect, but it gives you a sense of, for example, if you're looking at satellite galaxies, you're looking down at Ks that are, on the order of a few tenths or something like that in co-moving units. Okay, and then the C and B and large scale structure are not even on this plot, they're like over here, right? So this already gives you a sense for why, again, small scale structure is so good at tracing new dark matter physics. And then the suppression of power on small scales leads to underabundance of small dark matter halos throughout cosmic history. And by, and through that, the underabundance of galaxies, of small galaxies. Okay, so this is a plot made by Ethan for a study we've done a couple of years ago. Here is an example of the effect of dark matter baryon elastic scattering, velocity independent elastic scattering on the transfer function. And so one take home here is that as you decrease the interaction cross section, the cutoff appears at smaller and smaller scales. So as you lower the amount of interactions, you're only affecting smaller and smaller scales. So if your probes can access large scales, you can hide these interactions in that manner. Now, I just want to give you a very quick sense. Of course, we can take these transfer functions as computed by class or CAM, the linear Boltzmann codes that every cosmologist loves to run. So we can get them exactly. But as theorists, we can also kind of understand roughly what is the relationship between the scale at which the cutoff happens and in the interaction cross section. So I want to give you that sense very briefly. So the reason that the power is suppressed on small scales is due to collisional damping. So as dark matter couples to baryons and baryons couple to photons, at early times, dark matter is sort of prevented from falling into gravitational potential wells. And so the structure is smeared on scales that are small enough. And so one way to kind of guesstimate which modes in the cosmological perturbation theory are suppressed and which ones are not suppressed due to this collisional damping is to figure out what are the times when this collisional damping is relevant and when does the collisional damping stop. And the damping stops when the momentum transfer falls down to Hubble rate. So when the expansion of the universe becomes too fast in comparison to the rate of the collisions, the particles can no longer find each other. So the interactions will freeze out. And so the last perturbation mode that entered before the freeze out happens is the last one to be suppressed. So you can ask a question of what is the last mode to enter for a given interaction cross-section? So what was the largest mode that felt the suppression from collisional damping? And you can figure out the critical redshift at which this freeze out happens. And the last mode to enter at that redshift is the one that was of the size of the Hubble horizon at that time. Okay. And so that gives you the length scale, the K critical, below which the modes are suppressed and above which they're untouched by this interaction physics. And once you figure out the scale that relates to the mass of the halos that arise from these modes, and so observations give a upper limit on the minimum halo mass that we know, or the halos that we know exist in the Milky Way. And so from that limit, we can put a bound on the interaction cross-section. So we cannot have the interactions more intense than would allow for all the halos that we know exist to exist in our galaxy today. All right, so Ethan took this formalism and then actually did a full probabilistic analysis of all the satellite galaxies that we know from SDSS and the classical dwarfs, and then included also the DES and Pan-STARRS data. And from, roughly speaking, from the analysis that I showed you in the previous slide, he got a bound on the interaction cross-section as a function of dark matter particle mass. So the colored regions are excluded by the fact that we see no deficit of the dwarf galaxies in the local universe. Okay. The previous bounds from CMB, Lyman alpha forest, and so on are orders of magnitude weaker than what we were able to do with this analysis. Yeah, so this is for the velocity independent interaction. That's correct. And so I've been mentioning direct detection. So I just want to get your attention to the fact that here are direct detection bounds, but they look nothing like what you might be used to, if you're reading, Xenon 1 ton and so on papers. And that's because this is the very tip of that exclusion region. The actual lower bound is down here, 20 orders of magnitude lower. But one thing that's interesting about what cosmology provides is that it can go down to basically arbitrarily low dark matter masses, which are not visible in direct detection experiments. So we're really covering the parameter space that's beyond the reach of what we can do in a laboratory. And we're starting to kind of close that gap between these exclusion plots.
So Vera, I have a question, if you can hear me online.
Yes, I can.
Yeah, this is Anna. Yeah, so I was wondering about the I guess how important is the mass loss in the dwarf galaxies that they have experienced, because they're mostly satellites of the Milky Way, and kind of how do you map that to the original masses and kind of the cutoff in the power spectrum? Right.
So thanks for that question. For a detailed answer, I'm gonna punt it to Ethan for maybe after the talk. But for right now, I just wanna highlight that we've used the Galaxy Halo connection that they have developed for previous studies, and then kind of marginalized over all the free parameters within that model itself. So this was like a kind of a fully self-consistent probabilistic analysis where the parameters of the Galaxy Halo connection were free. and marginalized over to arrive at these bounds. But I do not have a detailed answer as to what the specific effect of the mass loss is. So I'm going to have to punt that.
No, that's okay. Thank you.
All right, thank you for the question. Okay, so moving on. So this was a story of what dwarfs can do for us in terms of dark matter proton scattering. In the case of the simplest scenario where there's no velocity dependence. So this is like the standard, WIMP-like dark matter. So we want to go further and we want to ask a question of, okay, what happens if you have velocity dependent scattering? This is certainly not the only model that dark matter could be. So I want to show you really briefly what happens in the cases where dark matter has a velocity dependent scattering with protons. So here is your universe, and here's the growth, the linear growth of dark matter perturbations in the universe that's free of any interaction. So dark matter potential wells are just growing over time. This is simulation made using the class code, so all linear stuff. And here is the case where dark matter interacts with baryons. And what you should take from here is that dark matter suffers through dark acoustic oscillations if you couple it tightly enough at early times. And you can do so particularly well if you have velocity dependent scattering. So in the case where there's velocity dependent scattering, your transfer function is no longer like that we know and love from warm dark matter, but it has these additional peaks at higher Ks. So you can no longer play the same game of saying like, okay, where's the cutoff? And then let's say, all the modes beyond that cutoff are suppressed. So we really need a way to take into account the fact that there can be this sporadic structures on smaller scales and understand what they can do to the observables that are nonlinear observables like satellite galaxies and so forth. So now I want to show you an extension work that was done by Karim Amari at USC in collaboration with Ethan and a whole bunch of other people. So what we did for this study is we wanted to avoid having to run any simulations. We wanted to see how far we can get with just the linear theory. So we took the observations from DS and PAN stars that give us a limit on the minimum halo mass. And we basically said, okay, we know the bound on warm dark matter from those observations. People have run warm dark matter simulations. We know how structure forms in warm dark matter scenarios. So let's assume that the transfer function cannot be suppressed more than the lower limit on the dark matter, warm dark matter mass allows us. Okay, so this transfer function corresponds to the lower limit on the warm dark matter mass. And a way to understand it is, I cannot observe linear matter power spectrum directly by observing dwarfs. But what I can do is I can say that whatever model I'm considering, if it messes with the structure more than this bound, so in other words, if I have, transfer functions that dip into this gray shaded region, they're disallowed because I would see more structure suppression than is currently consistent with observations of dwarf populations. And so Karim used the class code for a variety of velocity dependent models to figure out what are the cross sections as a function of dark matter mass where that severe suppression kind of happens in the transfer function. So we decided to very conservatively call all the models and all the cross sections that dip into this gray shaded region inconsistent with the data, because they would cause more suppression than is allowed. And we've decided to say that everything that pushes the first cutoff and maybe some structure farther out to the right where we don't probe, to scales that we don't probe with dwarfs, consistent with the data. Okay, so this is not likelihood analysis. This is just simply saying this is excluded and this is allowed. And doing just that simple step allowed us again to dip several orders of magnitude lower than the best current observational bounds on all of these velocity dependent scattering models than were than existed previously. So these different panels correspond to different velocity dependencies that are denoted by the power law index here. The gray were the previous limits from CMB, spectral distortions, and Lyman alpha forest. And then the blue is the analysis that we've done using this simple trick. Now, these are all numbers that don't necessarily, on the y-axis, that don't necessarily in themselves mean a whole lot. So to translate this, the scales that we're now probing with the dwarf satellites within the Milky Way are structures that arose from modes that entered cosmological horizon a few months after the Big Bang. Okay, so there's a sense in which we're now probing indirectly the physics that was taking place a few months after the Big Bang. And the current bounds imply that 1 in 100,000 interactions that every proton experienced at that point in time, at most 1 in 100,000, could have been with a dark matter particle. If there was more than that, we wouldn't see the dwarfs that we see around the Milky Way today. Okay.
Where power law, you have a prefactor, so where does that normalize to?
See, the V to the n power sigma naught, there's a C, there's a factor of C in there.
Right, so like you have cross sections for it.
Yes.
Be normalized to some extent.
Yes, that's correct. Yep. I want to say like order below a kV, like well below a kV. But I can work it out for you and tell you. Yeah. Something like that. Yeah. Well below the mass scale of the particles that we're probing because we don't want to deal with warm dark matter simultaneously. Yeah. All right. Now, next step is, like we've done an interesting thing with just the linear theory, like just being super conservative and saying like these guys must be inconsistent with the current data. But you can see that these kinds of transfer functions produce a ton of power suppression. Okay, so if you actually do the correct thing to do, which is if you run, in this case, an n-body simulation of a Milky Way-like halo. This is a cosmological simulation zooming in on one Milky Way-like halo in cold dark matter versus in interacting dark matter scenario, where we've put, like the transfer and the cross section, the transfer function in the cross section to the bounds that we derived in this conservative manner. You see a ton of power, a ton of suppression of structure. So like a lot of those little halos are washed out, which is expected, right? When you just skim the transfer function, you can tell that there's a lot of power missing. But this is just a way to a little bit more quantitatively say that if we actually model structure formation correctly using the simulations rather than relying on the linear theory, then we can do a lot better in terms of constraining these models, possibly a couple of orders of magnitude better. So this is the work that Ethan and Ruyan, our postdoc at USC, are working on right now. And then, of course, just to throw it out there, one thing that we started looking at very recently is what happens if beyond modifying the initial conditions for these interactions, so beyond ensuring that we start with a transfer function that's very suppressed, as it should be in these models, we also put in those interactions between baryons and dark matter into hydrosimulations. So this is something that we're starting to play with right now. And what this will give us is the ability to look at models. If you remember my old slide of these different models where momentum transfer rises as a function of decreasing redshift. So we would be able to look at models where the interactions happen as structure formation is ongoing rather than in the very early universe. So there's a lot of particle physics models where this becomes a really interesting question. So this is not yet a physical simulation. I just really like to have movies. So I put it in there in spite of Kareem, who's working on it, telling me not to do that. So this is not yet physical, but there's a lot of particle scattering. So I really like it. There we go. All right. Do I have questions at this point? Yes.
So matter dark matter something happens at the whole rate exceeds
the decoupling happens. Yes.
So what evidence would you need that it's not a There are events, but a cascade of events because you might have multiple dark matters.
Yeah, so we're not there yet. So what signature would you have? I mean, you would have a very, first of all, the imprint on structure formation would not be as simple as a single cutoff. There would be something more complicated going on. We haven't yet looked at something like composite dark matter models and so on, but this is really, really interesting. One thing that you can do is you can ask a question of if you let the momentum transfer be some arbitrary function of redshift, what is it allowed to be? So this is something that we can do with the data that we have, but then you have to combine CMB and large scale structure and small scale structure and so forth in order to cover Ks in a way that really recovers that kind of information. Yeah. Tony.
Another question on that was asking, is there any significance to the oscillations that you see in the rather than just the decline? Which sort of oscillation?
Yeah. Hi, Jimmy. So the significance of the oscillations is this is an imprint of the fact that dark matter was oscillating acoustically together with baryons in the early universe. This is those dark acoustic oscillations showing in the power spectrum. Okay. All right, I want to switch gears a little bit. I've talked about dark matter baryon scattering, but there are a lot of other non-WIMP-like dark matter models out there. And it turns out interactions are not the only thing we can probe with cosmology. We can also tap into other things that describe the physics of dark matter. For example, the phase space distribution of warm dark matter, which is something we don't very commonly talk about. So when we talk about warm dark matter, we're thinking, okay, so there is some dark matter particle sitting there in the early universe in the thermal bath. Everything's interacting at, the time in the universe was like a few seconds old. And so is dark matter with everything else. And eventually dark matter interactions freeze out, this particle falls out of equilibrium. And if it's so light that this happens very early on, it inherits a significant temperature and inherits some velocity that lets it stream out of gravitational potential wells if they're too small. And so that's the standard warm dark matter paradigm. And so one way for particle physicists to realize this paradigm is to say, well, what particles do we know in the standard model that are kind of warm? And it would be neutrinos because they're light and very weakly interacting. And they're a very convenient corner of the standard model to hide new physics because we know next to nothing about neutrinos. We can't even measure their masses yet. We're on a way to do that, but not quite. So neutrino sector is a convenient place to have dark matter emerge from in some way or other. And so back in the 90s, Donaldson and Widrow came up with this idea that, okay, so standard model neutrinos, 3 of them, are too warm to be dark matter. We now know that. So let's allow there to be another neutrino, but let's make this neutrino not interact to weak interactions. So this guy is not a thermal relic in the same sense that standard neutrinos are. But let's allow it to go through that mixing with active neutrinos. Active here just means normal standard model neutrinos. Let's let it mix, convert into active neutrinos and convert back, just like neutrino, eigenstates, flavor eigenstates are converting into each other. So neutrino oscillations, but now on steroids, right? And so like neutrino oscillations with a 4th one in there as well. Okay. And so the reason they did that is to allow this guy to be a little bit cooler and maybe be dark matter candidate. And so dark matter candidate that comes from sterile neutrino would be a mixture of the sterile and some flavor of active neutrino, maybe electron neutrino, maybe another one, okay? And there's some mixing angle. And if we make that mixing angle very small, there is a hope to make this a good dark matter candidate that's cold enough and that can be produced in the right abundance to constitute all of dark matter, okay? Now, dark matter candidate here written like this here has a definite mass. This is a mass eigenstate. Okay, so it has some mass that we could measure, just like we measure the 3 or attempt to measure the 3 normal neutrino masses. And let's allow that mass to be whatever it wants to be. Typically, we would assume that it's somewhere in the keV range, which is like a perfect warm dark matter candidate. Okay. Now, if you want the sterile neutrino to be all of dark matter, you need to set the mixing angle correctly as a function of the dark matter particle mass, and you need to live on this Donaldson-Widrow bound, this black line here. And here's the problem. The problem is that there are other observable consequences of having sterile neutrinos, and one is that they would radiatively decay and very slowly seep out X-rays from galaxies where they live. Okay, so from a whole bunch of X-ray observations of the sky, the Milky Way and other places, we have bounds on how much of that X-ray emission could there be from XMM Newton, from New Star, from Chandra, and so forth. And those bounds, excluded regions are colored here in blue, have like eaten up all of the available sterile neutrino dark matter parameter space in its Donaldson-Widrow original form. Okay, but people really like neutrinos and neutrino-based dark matter. So there's been more recent studies where people basically try to figure out a way to, instead of having this Donaldson-Widrow bound, to actually have a band of possible mixing angles where you can be all of dark matter and not be too warm in a sense and so forth. So in order to achieve this bound, this would be now a bound between the red lines here to produce sterile neutrino in the right amount, so not overproduce it and not underproduce it, make it in exactly the right amount to be all of dark matter. This study by de Gouveia and others have invoked self-interactions of the standard model neutrinos. Now, we know very little about neutrinos. We don't have a measurement of their self-interactions, but they could well be there without us seeing them, okay? So the idea here is, let's write down the simplest possible interaction through a scalar mediator particle. So we're including a new particle, okay? And let's let active neutrinos scatter off of each other by exchanging that mediator particle. Okay? Another thing that can happen if you write a vertex like this is that the mediator particle could be light. And in that case, you may end up with situations where it could decay into two neutrinos, or two neutrinos can annihilate into this new particle phi. Okay, so this is kind of, in a sense, a minimal extension of the standard sterile neutrino model. So add those interactions. And so what ends up happening when you add any kind of interaction like this, you, in a sense, reset the neutrinos more frequently in the early universe, and you increase the probability of them converting into sterile neutrinos right after or right before the interaction. It's like introducing an additional measurement of the neutrino flavor, and you may end up, you have more chances to catch this neutrino in the sterile state rather than in the active state. So this is basically a way to lower the mixing angle, to lower this conversion probability, okay? Depending on the mass of the mediator, and expand this band where your theory can live. Okay. All right. However, as these neutrinos, as these sterile neutrinos are produced, depending on the mass of the mediator particle, they inherit very different phase space distributions. And so we asked the question, this is work done by Ruyan and Ethan and collaborator. We asked the question, okay, so for these different phase space distributions, what would the bounds on the mass of this warm dark matter-like candidate look like from just the dwarf galaxies? So we took the same, the same data that gave us the bounds on standard warm dark matter, and we swapped out the phase space distribution that's appropriate for these models where neutrinos feature a self-interaction. And these are the bounds that existed before. Right? This is a plot made by Rui. And we've been able, with combination of particle collider bounds and bounds on the mass from satellites, on the mass of this kind of warm dark matter, we were able to exclude the situations where the interaction proceeds through a heavy mediator particle that's heavier than a GeV. Okay, so in other words, in terms of the theory, this option is no longer viable. And then, you know, if you allow light mediator, we also close off a lot of this allowed parameter space and can play the same game. Okay.
So in this plot, what's the best mass of a regular?
60 millielectron volts is like the sum, so this would be a heavy guy. Yeah. Yes, all dark matter is the same. Yeah, yeah, totally fair question. All of these bounds weaken when you mix different things, right? So if you have a fraction of dark matter that behaves in this way, your bound drops very quickly. It's a totally fair question. All right. How many more minutes do I have? 10 minutes? Okay. Okay, I'll give you a taste of some new results from 21 centimeter intensity mapping and then invite you to ask me more if you're interested. So going back in Redshift, one other probe that has emerged as like very complementary to everything we look for when we look at structure formation, we look at the local structure, is the 21 centimeter line from neutral hydrogen that you would measure at cosmological distances. So in IGM between recombination and reionization. So we're talking really high redshifts, order 20. And so the idea there, as probably most of you know, but just for very quick recap, is that neutral hydrogen has a spin flip transition. And that transition corresponds to the emission or absorption of a photon at 21 centimeter rest frame wavelength. And the intensity of that emission or absorption will depend on the populations of the excited versus the ground state of hydrogen. And that ratio of the populations is quantified, parameterized by something called the spin temperature, okay? So here is a plot of standard cosmology, various temperatures. Red one is the spin temperature. And the spin temperature is a function of redshift. The spin temperature depends on a whole bunch of processes, radiative and other processes. So for example, radiative transitions, the absorption and emission of CMB wavelength photons, the atomic collisions, the Lyman alpha background or Wujheisen field effect, all of these will jiggle around this red line. And sometimes the spin temperature couples to that of photons, the blue line here. At later times, the baryons decouple from photons. So this is the temperature of baryonic gas, the hydrogen gas. So at later times, the spin temperature couples to baryons, then it'll recouple to photons. And then when the stars turn on, the spin temperature will couple back again to the temperature of gas and so forth. So all this to say, there's a whole bunch of processes that control the spin temperature of atomic hydrogen. And at a redshift of around 20, it's been predicted for a really long time there would be an absorption trough. So when you take the difference between the CMB and the spin temperature, you get something called the brightness temperature, and you get a dip on the background of the CMB black body spectrum. Okay, and so in 2018, the EDGES collaboration reported something that looked like a measurement of this absorption trough. And the depth of this trough, in a sense, signifies the recoupling of spin temperature to that of baryons. So at that redshift, around this redshift, enough Lyman alpha radiation starts to be around from star formation that the baryons, which have been cooling away from photons, cooling adiabatically, are colder, and the spin temperature couples to them through Lyman alpha absorption and emission. And so the depth of this trough, in a sense, measures the temperature of baryons at these really early times. So it measures the temperature of gas in the universe. Okay? And the interesting thing about what Edges found is that this trough was twice more as deep than would have been predicted in standard cosmology. And that's not something you can do. That's not something you can get unless you cool down baryons more than they should have cooled through, just the adiabatic process. And so a way to cool down baryons is to couple them to something colder that's around at that time. And cold dark matter is an excellent candidate to seep out the heat from gas. So this measurement was immediately interpreted by a whole bunch of studies as possible indication that there are interactions between dark matter and baryons that are happening at those redshifts and cooling down the gas. And the kind of interaction that you would need for something like this is one that does this coupling at late times, so negative powers of velocity dependence. That was kind of like the leading, cosmological explanation for what this might be in terms of new physics. Now, there's a lot of issues with this measurement. There's been measurements after it that have not confirmed it and so forth. But what happened when Edges reported it is that there was a whole spark of interest in these dark matter models and in 21 centimeter global signal as a probe of dark matter physics. And so what happens when you couple dark matter to baryons is that your global signal, as you increase the strength of coupling, the global signal becomes deeper and deeper. And so from this measurement, from Edges collaboration, paper by Barkana came out saying that, look, you have to have interaction cross-section above this yellow, so like within the blue region, in order to achieve such a depth of the signal. Okay? You have to have strong enough interactions of this kind to explain that signal. Okay. All of these previous studies, however, have only taken into account the exchange of heat between dark matter and baryons. What they haven't taken into account is all this beautiful stuff that I was telling you about, where dark matter baryon interactions affect structure formation as well. So this is work by student Trey Driscoll at USC, where he basically incorporated primarily the effect of structure or suppression in the same models, self-consistently together with the heat exchange. So if you have dark matter that scatters with protons at redshift of 20, the power spectrum that you would end up with, depending on the interaction cross-section, is suppressed in this characteristic way. So in particular, this plateau in this region is something that will end up affecting the global signal, because the global signal is driven by Lyman alpha radiation that comes from halos that host galaxies. So if you erase those galaxies from existence or suppress their numbers by doing this suppression, you are disabling that same coupling that would give rise to the global signal. I'll skip over some of the details here in interest of time. And here's the halo mass function in these modified models. You see a broad suppression on a wide variety of scales. And then what Trey did is he used Galacticus in collaboration with Andrew and Ethan and figured out what does the population of halos at that high redshift look like in these interacting models. And so what he arrived at is the following. So here is the global signal. The blue line corresponds to the standard calculation that was present in literature before, where you just fold in the heat transfer between the fluids. And if you take into account the suppression of power, you end up getting the blue line, which delays the signal to later redshifts and also makes it much, much less deep than was previously thought. So this is a correction in on the theoretical calculation of the signal itself. So nothing having to do with the data yet. But then you can ask a question, okay, so let's say that I wanna make Edges a viable explanation for these interacting models. And let's be very loose in what we mean by viable. Let's require that the bottom of this trough of the global signal is just roughly in the right range of frequencies and at the right depth. So let's just hit this window with that bottom line data point there. What do we need to make the cross-section to be as a function of dark matter mass. Okay. And so just from that requirement, these colored lines are consistent. All the gray ones are for cross-sections and masses that are not consistent with this data. And so Trey's results have basically narrowed down the viable parameter space to this white region over here. The hashed region is excluded by the CMB bounds. So there is a very, very slim sliver of the parameter space that you can put these models in and explain edges with a Coulomb-like interaction. All right, I will skip over the many rest of the slides and just put up the conclusions, of which I've covered the first half. But basically, near-field cosmology provides some of the best bounds on dark matter interaction physics. But we're at a point where we've exhausted what we can do with analytic theory, and we really need to start doing predictions in a self-consistent manner, doing cosmological simulations. And I've also told you a little bit about 21 centimeter cosmology is a new frontier in terms of probes of the dark matter physics. And one interesting finding that we found recently is that Coulomb-like dark matter has only a tiny bit of parameter space in which it could possibly explain the edges signal, whereas many of the other leading models are completely excluded. I will finish with that statement that dark matter is a hard problem that necessitates collaboration between various subfields of cosmology, astroparticle, simulation, observations. And with that, we are organizing a program at KTP in 24 in the summer that attempts to bring all of these communities together. So you guys are invited, welcome to apply and participate. And yeah, I look forward to this. Thank you very much.
Questions for Vera here or online? See a hand from Josh online. Josh, do you want to start?
Yeah, so Vera, with what you were talking about right at the end with models that are consistent with the edges signal, so what are the prospects for ruling out that one remaining band that is currently allowed? What would it take to do that?
Yeah, so the hope is that these global signal measurements will become better in the coming years. There's several experiments that are attempting to do these measurements. One big challenge is, as I'm sure you know, is getting a handle on the foregrounds that's good enough that we can trust those measurements. So the easy thing is if we, if we're very, generous about how we model the foregrounds and we just put the bounds. The harder thing is if we see a signal, of course, then it becomes a question of how well we're modeling everything. But they're good prospects for the global signal. We're doing forecasting exercises and other students working on this at USC. I will have an answer for you more quantitatively, maybe in a month or so. But for right now, also just to mention that there are a lot of experiments that are trying to measure the power spectrum of the 21 centimeter fluctuations, which is sensitive to the same physics. So I think it'll be interesting to see what they can do, because their resilience to the foregrounds in terms of these kinds of measurements is probably better than that of the global signal. So that's all to say. I don't know quantitatively, but it's a very small sliver of the allowed parameter space that we should be able to close in the future.
So you mentioned that you're now close.
Say it again? Sorry.
You said that we are close to directly measure the masses of neutrinos.
Yeah. Mm-hmm.
So for those experiments, are they also able to measure masses that detect sterile neutrinos?
Yeah, so the measurement of the masses of neutrinos would come, so that reference was specifically to the next generation CMB experiments from the ground that would measure the sum of the masses. Okay, so the KV scale sterile neutrino would not be doing the same thing as much lighter active neutrinos. So it wouldn't be transitioning to being non-relativistic in recent history and therefore changing the structure formation at late times, which is what the CMB experiments are after. The sterile neutrino could be better constrained by, exploration of the small scale structure. So it's a different kind of physics that drives one and the other mass bound. Yeah. But one of the goals of the Simon's Observatory is the measurement of the sum of the neutrino masses. So within the next, 5 years to a decade, we're really aiming at having that number.
One more question. Okay, if not, let's thank Vera again.